Hello everyone. In this section, we are basically starting the third or the fourth section of the book, which is on file systems. So this is chapter number 36 of your book, Operating System 3 Easy Pieces. So we are going to study about file systems, and file systems, as you know, are stored in hard disks. Hard disks are considered as IO devices. Okay, so input-output devices basically is a general category of devices which are attached to the computing systems, and they can either send data to the processor or receive data from the processor or the computing system. Okay, so these are called input-output devices. So there's a broad category of them. Lots of them. Basically, apart from your RAM, everything that is attached, that you can see attached to your computer, is considered an IO device by the processor. So there are typical IO devices that you know, input devices like keyboard, mouse, etc., and output devices like monitor, speakers, etc. Hard disk is also an IO device. The processor can either read data from the hard disk or send or store data to the hard disk. So we will start by studying the general characteristics of the IO devices, and then we'll move on to hard disks and then study how file systems are stored and files are maintained on your hard disks. So let's start. Can you imagine any program without any input or a program without any output? So think about it for a few minutes. Like, what would a program look like if it does not take any input? And input means anything. It doesn't read from the keyboard, it doesn't read from the mouse, it doesn't read from the hard disk, it doesn't read from any other IO device. And similarly, another program that basically does lots of calculation and it does not give any output. Okay, so if a program is not doing any output, all the work that it has done, what was its purpose? I mean, what information was it supposed to conclude that it was not giving output to anybody else, and it was storing the result of its computations with it inside itself. Okay, so you can come up with some contrived examples, but you will see that it is difficult to have a program that doesn't do IO, input output. Okay, most of the programs that you can think of, they always do input output. So input output is a very essential activity in our computing systems because users communicate with that computing systems through IO devices or input output. So what does a typical system looks like? We have this CPU, and then we have this memory. Okay, so this is still valid. We have a CPU and memory in our system, which we call RAM. So like some 20-30 years ago, a typical system hierarchy would look like this. The CPU and the RAM or memory, they will be connected by a high-speed bus. Let's call it a memory bus. So memory bus is a high-speed device basically which connects a CPU with memory. Okay? And it is usually proprietary. Every computer manufacturer or processor manufacturer has their own hardware for connecting CPU to memory. Okay? So memory buses are proprietary technology. And then there will be a general purpose IO bus which will basically link your uh, CPU and your memory to other devices which are like graphics card, etc. Okay, so some of this basically example of this bus, one of example is PCI, peripheral component interconnect, which you can connect different devices to your computer. Okay? So this kind of bus we call it general purpose IO bus. And then there's another bus, let's call it peripheral IO bus, which will connect further devices with your computer systems. Okay, and the devices that they will connect here, these cylinders are usually used to represent hard drives, okay, or permanent storage. So here, let's say they are connecting different hard disks or different USB devices to the computer. Yes, and examples of this peripheral I/O bus are this SCSI, SATA. You must have heard these names in relation to hard disks. These are the connectors that connect hard disks to the computer or motherboard. And similarly, a USB connector which helps connect USB flash drives to your motherboard. So if we consider this thing as a hierarchy, what difference can you make between these different type of buses? We have seen what kind of devices these buses are connecting to the computing system. Okay, this bus is used to connect memory to the computing system. This is used to connect graphics card, LAN card, etc. That kind of systems to the computing system. And this bus is used to connect hard drives and USB flash drives to the computing system. So what can you guess from this level of hierarchy? What can you guess about different properties of these buses? Let me give you a hint. Think in terms of speed. Okay. So take a couple of minutes and think in terms of speed. What will be the difference in characteristics in terms of speed of data transfer in these three types of buses? I hope you were able to guess that uh, these devices that are connected to these buses operate on different speeds. So memory RAM is the closest to CPU and it needs to operate on very high speeds because CPU is constantly accessing memory. So this bus, the memory bus, must be a very high speed bus. It should transfer data at a very high data rate or transfer rate. In the middle, we have, or on the other end, we have these buses which are connecting peripherals to the computing system. So most of the peripherals, they are quite slow. The speed of hard disk is like 1,000 times slower than the speed of RAM. Okay? So these devices will be very much slower compared to memory devices. So this bus needs not be very fast. It can operate at very slow data transfer rates, and basically it's much cheaper to manufacture such buses. So this bus is the kind of the slowest bus on the system. And in the middle, we have another bus which connects devices which basically do not need to be as fast as RAM and cannot afford to be as slow as hard disks. So graphics card, network card, etc. These are connected to this general purpose I/O bus whose speed is in the middle of memory bus and the peripheral I/O bus. Okay. So this is a hierarchy in terms of speed, which bus is faster than other and which devices are connected to which bus. So this is the hierarchy that we could see in our systems like some 20 years ago. Okay. So these days, if you look at the hierarchy that exists these days, it looks something like this. So one difference you would notice is that the graphics card, now it has a special bus which instead of being connected to PCI bus with the LAN card, etc., it has a special bus. This is because graphic systems have become powerful and they need a lot of computation, so they need a high speed link to the CPUs. Okay, so this is in result of a lot of it is because games have become very popular, and secondly also our displays are much more higher resolution today compared to 20 years ago, and therefore there needs to be a lot of data transfer between the graphics card and the CPU to either make your games go faster or so that your displays are refreshed at a at their appropriate rate. Okay, so graphics cards need a high speed connection to CPU these days. So we have this PCIe, the PCI Express bus, which connects the graphics card to the CPU. The memory interconnect, similarly, it's a high-speed bus which connects memory to the CPU. And then here we have a whole subsystem, a chip specially designed to connect all the other peripherals to the CPU. Okay, so instead of these peripherals connecting directly to the CPU, they connect to this I/O chip, and then this I/O chip, it plays a role of an intermediary between the CPU and all these disks. So this I/O chip then uses different kind of buses to connect different devices to itself and indirectly to the CPU. Okay, so you have this eSATA for disks, USB for this kind of peripherals, and PCIe, etc. for network and graphics card. So this is the internal structure of your motherboard block level diagram, how it would look like at a very simple level. Okay. Again, there are differences of speeds between different buses because that depends on the device that is being connected to that particular bus and at which speed that device will operate. So how does a typical device communicates with the CPU? So typical, or the IO chip in this case. So a typical device comes with an interface. Okay, interface, as you know, is an abstraction which gives access to the device behind that interface. Okay, so an interface of a device typically looks like this. It has a few registers that are visible to the CPU, and the CPU can basically read from these registers and write data in these registers. Okay? And behind this interface hides the whole device. So the device can be anything. It can have any hardware, controllers, RAM, any chips, etc. But that depends on the working of the device. So device will internally perform its work, but to use to communicate with the CPU or the computing system, it will use basically this interface. Okay, so a set of registers through which data will be exchanged between the CPU and that device. So device can also read and write data from these registers, and CPU can also read and write data from these registers. So basically when we connect our device to the computing system through a bus like USB or eSATA or PCIe, whatever, we are basically connecting this interface to the motherboard interface so that CPU can get access to and read and write data in these registers. So these registers, there can be many registers in an interface, but we can broadly classify them into three kind of registers, three categories. Okay. So one of them will be category of status registers. Status registers basically have some flags which indicate the state of the device. Okay. Through this device, through this register, the CPU can read data and know about the status of different states of this device. Okay. So a device basically, when it moves from one state to another state, it will basically change bits in this status register to inform the CPU of its change of status or change of state. The CPU can read this status register to know the current status of the device and at which state it is now. The other two registers are other two type of registers are command type of registers and data type of registers. So command type registers, as you can guess from the name, that through this register CPU can write different commands in this register and give different commands to the device. So take an example of a hard disk, okay, which is an IO device through which CPU can read data and write data to the hard disk. So the commands for this device would be a read command, a write command, etc., etc. Okay, so different type of commands the CPU can give to the device by writing those commands in this command register. And similarly, if you continue with this example of a hard disk, then this read or write commands, they will involve different data. Okay. So CPU will either read data from the hard disk or write data to the hard disk. So these data registers can be used to transfer data with these commands. Okay, let's say if CPU want to write data to the hard disk, then it will basically give a write command, and the data that it want to write to the hard disk, it will write it here in this data registers. So internally, the device will read the write command, and then it knows that CPU wants to write data, so it will read data from this register, these registers, and store it inside itself. Okay. Similarly, for read command, vice versa, CPU will give read command to the data, read command to the device, and the device will transfer the data that the CPU is asking for in these data registers, from which the CPU can then read data. Okay. So these command and data registers will be used to give commands to the device and transfer data to and from the device. So this is a general kind of interface that every device would have. The number of registers may vary, the sizes of the registers may vary, but typically we will have these categories of registers. So what's a typical protocol that a device uses to communicate with the CPU? So a CPU is continuously checking the status of the device. While the device is busy, status registers tell the CPU that the device is busy. This means the device is already performing some work and it cannot accept any more commands right now. So while the status is busy, the CPU doesn't do anything. It just waits the device to become free. Okay, so it waits for the device while it is busy. So once the device is free, it will change its status and status will no longer be busy. So the CPU will get out of this loop. And now if it wants to communicate with the device, it will write data to the data register and then write command to the command register. And once it writes command to the command register, the command is transferred to the device, and device will again start working on this command, and device will again become busy. Okay, so again, while the CPU, the device is implementing this command and doing work on this data, the status of the device will be busy, and CPU again knows that now the device is busy and it cannot accept any more commands, so it will wait, and this cycle will continue. Okay? So device will either be busy or free. When the device is free, then CPU can pass commands to the device. So a typical thing that the CPU is doing is continuously monitoring the status of the device, okay, to know whether the device is busy or not. So there are two ways in which CPU can monitor the status of the device or get information about the status of the device. One is that it continuously reads the status register of that device, okay, like in this loop. It continuously reads the status register and checks whether status is equal to busy or not, and if it is busy, it continues in this loop. Okay, so this technique of continuously reading the status register to know about the change in status is called polling. Okay, we say that the CPU is polling the status of the device continuously. Okay. Now polling is a effective method, but the disadvantage of polling is that it keeps the CPU continuously busy. Okay, CPU is doing nothing but executing these instructions while waiting for the device. Okay, so this is costing us basically costly CPU instructions. CPU is kept busy polling the device, while if we had some other method to know about the status of the device, then CPU we can release the CPU of this polling and CPU can do some useful work. So secondly, so polling is a device which is wasteful of CPU time. Secondly, when you have to transfer data between the device and the CPU, like we are doing here, writing data to a data register, this is again done by the CPU. So if the CPU is involved in transferring data from RAM to the device data register, then this kind of I/O is called programmed I/O. Again, basically our CPU is being involved in a task which is not too compute intensive. Okay, transferring data is not a big task from RAM to the device register. But our CPU, which is a very powerful device, it is being involved in this data transfer, and we can say that this is also kind of a waste of CPU time or CPU cycles, because this task could be performed by some other device, and CPU could have done some more useful work. So here in this particular protocol, there are two problems. One is that CPU is continuously polling the status of the device, which is consuming CPU time, and again CPU is doing programmed I/O, which means CPU is also involved in transferring data from RAM to the data register, which is again a trivial task and is wasting CPU time or CPU cycles. So polling is inefficient and program I/O is also not very efficient. So the counter to these two problems is that for polling, instead of CPU continuously polling the change in status of the device, we can use interrupts. Okay, what we can do is the CPU can write the command, and then CPU can, instead of polling, CPU can go and do some other work. Okay, so device will get busy and it will do its work, and when it is finished doing the work, device will send an interrupt to the CPU, and that way CPU will know that now the status of the device has changed. Okay, so instead of waiting for the status to change and polling the status, the CPU can now forget about the device and go ahead and do some other useful work. The device, while it's busy, it continues its work, and once it has finished the work that was assigned to it, it will send an interrupt to the CPU. And CPU, as we know, when the interrupt arrives, whatever the CPU was doing, CPU will get interrupted and jump to the interrupt handler. In the interrupt handler, the CPU can check, okay, the device has finished the work and its status has changed, so it can do whatever it was supposed to do on the change of the device status. So it can either issue a new command or do whatever it wants. So the device will raise an interrupt and the interrupt handler will be called. Here interrupt handler is called basically interrupt service routine, ISR. Okay, so ISR basically is the same as interrupt handler. So the CPU will run OS code and it will check that the device has finished its task, and then it will wake the process which was supposed to check the result of this IO. Okay, and then the process can do whatever it wants with the CPU or the device. So basically, using interrupts, we relieve the CPU of polling, and the cycles that CPU was wasting in polling, continuously reading the status of the device, it can put those cycles or that CPU time to some other useful work. So this was the situation with polling, that this, let's say, process 1 was executing and then it issued an IO command, and while the device was busy doing IO on behalf of process 1, CPU was continuously polling. Okay, it was continuously polling, and then once the device had finished, status changed, the process 1 can basically continue its work further. With interrupts, it becomes like this. Process 1 executing, it issued an IO, and while the disk was busy doing IO for process 1, process 1 gets sleep, it gets put to sleep, and the CPU can, instead of polling all this time, CPU can do some other useful work. For example, it can run process 2 during the duration of this task or this IO that the device is performing, and once the device has finished IO, it will send an interrupt. At that time, interrupt service routine or interrupt handler will run, and the operating system will deschedule process 2 and run process 1 again. Okay, so this time, which was all spent in polling, now it can be put to some useful work. So this is why interrupts are used in the processors when commuting with I/O. Okay. So interrupts are especially useful for slower devices. Okay. For faster devices, polling might sometimes be better, because interrupt, as we have seen, interrupt involves context switches. So if the device is fast, then the cost of the context switch might be more expensive than polling. Okay, so if the device is very fast, then it's sometimes better to do polling. But mostly I/O devices are very slow, so it's better to use interrupts with I/O devices. Another problem with interrupts can be that if the device is very fast, let's say you have a network card which is very fast, and with the arrival of each packet, an interrupt is raised. So it can happen that a packet has arrived, interrupt was raised, the interrupt handler was called, and while you were executing that interrupt handler, another packet arrived. Another packet arrived, the first interrupt handler is not finished, another interrupt is raised, so the same interrupt handler is called again, and again, before that interrupt handler has finished the second time, a third packet arrives. So in this way, the interrupts basically continue to happen, and the packets arrive very fast, and each packet raises an interrupt, and before the previous interrupt handler has finished, another interrupt is raised, and the interrupt handler is called again. Okay? So we can get stuck in this kind of lots of interrupts arriving together and interrupt handlers being called. So in this case, we can use a technique called coalescing. Basically, instead of raising an interrupt on each packet, we can have a buffer when the packets arrive, we continue to save those packets in that buffer. And let's say the buffer can accommodate like 20 packets. So once there are 20 packets in the buffer and the buffer is filled, only then do we raise an interrupt. Okay? And while the interrupt handler is called for these 20 packets once, while it is processing these 20 packets, we can use another buffer to store the next 20 packets. Okay, and by that time, hopefully, the interrupt handler for the previous 20 packet has finished. And when this second buffer is filled, then we can raise another interrupt, and the interrupt handler can service these next 20 packets while we store the packets that come after that in the first buffer. Okay, so this can be coalescing, mean we basically collect some packets together before raising an interrupt. Okay, instead of raising an interrupt every packet, in this example, we'll raise an interrupt every 20 packets. Okay, so this will give some time for the interrupt handler to complete before the next interrupt is raised. So programmed I/O again, as we discussed, is a technique where the CPU is involved in transferring data from the RAM to the device registers or vice versa. So I/O transferring data is again a trivial operation, and CPU is a much more powerful device. So uh, CPU being involved in transferring data from RAM to device register or vice versa is kind of a waste of CPU cycles. So again, if we could have some other device which can basically perform this I/O for us, this transfer of data from RAM to device registers or vice versa for us, then we can relieve the CPU from this programmed I/O, and the CPU can go ahead and do some useful work. Okay. So let's see, we have this process 1 running, and it wants to transfer some data to the device. So it is basically doing this copying of data from RAM to the device registers, and it is being done by the CPU. Okay. As we said again, this programmed I/O is a trivial operation, and it is a waste to involve CPU in this programmed I/O. So how can we proceed about this? So again, the hardware manufacturers, they have basically device or invented another device which is called direct memory access. It's a small circuit which can basically transfer data from RAM to the device registers or vice versa. Okay. It's a very small circuit, and it operates in such a way that you give it the source address, the destination address, and the amount of data to transfer. That's all. And then it will be activated, and it will basically transfer that data from the source address to the destination address. And after it has terminated, it will finish. So it's a very simple circuit which is basically involved found in most motherboards, and it can transfer data from RAM to the device registers or vice versa, independent of the CPU. Okay. What the CPU does is it just gives the source address and destination address and the amount to transfer to the DMA, and then it can go ahead and do some useful work. The actual data transfer will be done by the DMA instead of the CPU. Okay. So here we have the CPU process 1 is executing. It just writes the command to the DMA, the source and the destination, and this data transfer, data copying from RAM to the device or vice versa is done by the DMA instead of the CPU. Okay. And in this time, the CPU can go ahead and do some useful work. Okay. So DMA basically relieves the CPU of transferring data from RAM to device or vice versa. Okay. So again, as I said, it's a simple circuit, hardware circuit, which is found in most motherboards, and it basically relieves the CPU of doing these data transfers. So again, programmed I/O, we can avoid it by using a DMA. So how does the CPU communicate with the device? How does the CPU write these data and command registers of this device, and how does it read the status register of the device? There are two methods. Historically, there have been two methods. One is that the CPU instruction set contains special instructions for reading and writing data from device registers. Okay. This is a very old concept, and old processors in their assembly instructions, they had special instructions or explicit IO instructions which were used to read data from the device registers or write data to the device registers. Okay, so all the status, command and data registers, we had special uh, instructions in assembly language of processors to read and write data to and from these registers. So this technique needs special instructions in the assembly language to read and data to device registers. And another technique is called memory mapped IO, and in this the registers of each device are mapped to some addresses in the address space of the processor. Okay. So instead of having special instructions to read and write data to the uh, device registers, the processor uses simple load and store instructions on those special addresses in the address space to read and write data to the device registers. Okay, so device registers are mapped to special addresses in the address space of the processor, and instead of having special read-write instructions, processor just uses simple load and store instructions on those addresses to read and write data to the device registers. Okay. So as you can see, the memory mapped IO makes the hardware simple, hardware of the processor, because processor does not need to have special IO instructions for these device registers, and it can use load and store instructions to read and write data to the device registers using those special addresses. So in most modern systems, it's a memory mapped IO technique that is being used. So there's another problem that the operating system faces, is that the operating system writers, when they are writing the operating system, they do not know which device will be which kind of devices will be connected to this computing system, and how do we read and write data to those devices, because each device has its own protocols of writing and reading data, its own commands, its own set of registers, etc. For example, data writing on a rotating hard disk is another, will follow another protocol, and data writing on a USB flash drive will follow another protocol. Okay. The operating system writer does not know what kind of devices will be connected to this computing system, and therefore cannot foresee or program for all kinds of devices. So how should the operating system manage all those devices, and how should it ensure that the file system should work to store files and directories, whether it is on the rotating hard disk or whether it is on the USB flash drive? So how does it do it? Again, the answer is the operating system's functionality is divided into a layer of abstractions, and at the lowest level we find a device driver. Okay. A device driver is a layer that hides the internal or operational details of every device. And even though the operating system writer does not know how a device works, or how do we write and read data in that device, because every device can have a different protocol, but the manufacturer of that device does know how does my device stores data, and how can data be read or written to my device. Okay. So each manufacturer, when it provides a device, it also provides a piece of software called a device driver. Okay. And a device driver is here at the lowest level of the hierarchy. So the operating system commands, read or write, they basically pass through different OS layers, and they arrive at this device driver layer. And then the operating system command will be either a read command or a write command. And then the device driver of each hardware device will basically translate that read or write command into a proper series of steps that are needed to write data or read data from that particular device. Okay, so it will basically transfer the read and write command to the specific protocol which is needed to do read and write operation for that particular device. And the device driver is provided by the device manufacturer. So The device manufacturer has all the details about the device and the protocols needed to read and write data to that device. So therefore, the device driver at the lowest level of abstraction will translate the OS commands to the proper, basically, protocol needed to read and write for read and write operations on that device. Okay? Otherwise, the operating system at the very highest level, the programmer only uses this simple API: open, read, write, close, etc. The programmer does not know whether this data or file is located on a rotating hard disk or on a USB flash drive or on some other device. So all these details are handled through this operating system layers, and at the lowest level, the device driver will basically convert these operations to the proper steps or protocols which will be specific to that device. So this is a general overview of what are I/O devices and how they are connected to the computing systems and how does the CPU communicate with these I/O devices. Next, we will basically move on to a specific type of I/O device, which is the hard disk, and see how does a hard disk works and how it is connected to the CPU and how does it work internally. Again, if you have any questions, you can basically start by reading this chapter number 36 of the course book, and any questions you can ask them in the interactive session. Thank you very much.